Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to talk about how to interpret the weights of a neural network. You'll notice that in previous courses, linear regression and logistic regression in particular, interpreting the weights was pretty straightforward. With neural networks, this is not the case. Neural networks have faced criticism for not being easily interpretable. However, we will learn that this lack of interpretability is not a limitation of neural networks, but rather a limitation in understanding of geometry. In other words, it's not that neural networks are not interpretable. It's that the people who are criticizing neural networks for not being interpretable don't understand geometry well enough to understand why it's ultimately their way of thinking that is limited. Let's start by reviewing how to interpret the weights of a single neuron, since a neural network is just a layer of neurons. Let's start out with a simple model. Suppose we are trying to predict whether or not a person is at risk for disease X. The inputs to this model are obesity, whether the person smokes or not, and how often they exercise. Suppose the weights for each of these factors are +1, +0.5, and -0.8. What does that tell us? Well, let's try it. Take a person who is not obese, smokes, and exercises daily, so the input vector is 0, 1, 1. The output of the logistic regression is sigmoid of 0.5 minus 0.8, which is the sigmoid of minus 0.3, which is 42.6%. So the probability that this person is at risk for disease X is 42.6%. Since this is less than 50%, we would make the prediction not at risk for disease X. At this point, it should be clear how these weights affect the output. There are two characteristics we care about for each weight, its sign and its magnitude. The two relevant factors for our test subject is that the person smokes and exercises daily. One of these is clearly bad and one of these is clearly good. We can see this because the weight for smoking is positive, leading to a higher chance of disease X, but the weight for exercise is negative, leading to lower chance of disease X. However, magnitude matters as well. The magnitude for exercise is 0.8, but the magnitude for smoking is 0.5. So exercise will overpower smoking, and the final probability will be less than 0.5. Now, this is fine for linear neurons, but what happens in a neural network? The problem is, past the first layer, the weights do not really have any physical meaning. For example, the first hidden unit could be 0.5 smoking and minus 0.8 exercise, but the second hidden unit could be minus 0.1 smoking and plus 0.3 exercise. The problem is that, because neural networks are so expressive, they lose this simple interpretation past the first layer. Remember that passing a value through an activation function, like sigmoid or tanh, flattens out extreme values. In other words, they are nonlinear. That means you can't combine the two smoking weights, plus 0.5 minus 0.1, to be 0.4, because that disregards the nonlinearity. Removing the nonlinearities would be pointless, because that would just bring us back to a linear neuron. What makes neural networks so powerful is that beyond the first layer, the weights no longer represent the initial inputs, obesity, smoking, and exercise. They are powerful because beyond the first layer, the weights represent something different entirely. Something that cannot be expressed as just this much obesity, this much smoking, and this much exercise. In other words, the very fact that you cannot express the meaning of the features beyond the first layer in terms of the real inputs is what makes neural networks good at what they do. At the beginning of this lecture, I mentioned geometry. We haven't gotten into that yet, so let's get into it now. When people talk about interpretability, they're usually referring to two types of models. The first is the kind we just talked about, the linear neuron, where each weight can be interpreted as how much that input affects the output. The second kind is a decision tree, which essentially boils down to a bunch of if statements. For example, we could say, If obesity is greater than 0.5 and smoking equals true, then return 0.75. What do these mean geometrically? Well, a linear model is called a linear model because the data between each class is separated by a line or a plane. We call this line or plane a decision boundary. A decision tree works using if statements. Because of this, the decision boundary always has to line up with the coordinate axes. You can see how these decision boundaries are not very expressive. For example, what if we want to find a decision boundary like this? This is something a neural network can do, but a linear neuron can't do without putting in a lot of hard work to manually engineer features, which may or may not themselves be interpretable. So trying to interpret what a neural network does in terms of its raw features is basically the wrong question to ask. Because if you do that, you're essentially limiting the model's geometry to be a straight line. So forget about trying to interpret the classifier in terms of rules based on the raw inputs. A better question is, what does the decision boundary look like? In later courses, when we start looking at images in depth, we will learn yet another way of interpreting the weights of a neural network. This is going to happen at a much larger scale, since images have very high dimensionality. What we will eventually see is that neural networks learn a hierarchical representation of the data. A very common example is learning to classify faces. The first layers of the neural network will learn to identify basic strokes. The next few layers will learn to identify parts of faces, like eyes, nose, lips, and mouth. The final layers of the neural network will then put these individual facial features together to form full faces. The main theme behind this is that as you go deeper and deeper into the network, the features being learned get more and more complex. In other words, the deeper the network, the more complex the ideas it can represent. This is why so much neural network research tends to focus on images. Images are easy to interpret because naturally, you can look at them. So what is the central message here? Well, it's that if you want to interpret the weights of a neural network, it doesn't always make sense to look at one individual weight at a time. That one individual weight represents how important a feature is, but that feature could be a highly nonlinear combination of the inputs with no real-world interpretation. However, when we look at images, we're looking at weights in aggregate, and we're looking at how, given these weights, what images activate particular neurons. Those images represent what a neuron has learned.